Today being a Father's Day, this episode is dedicated to all the fathers out there. Hey guys, Nachkazi here. In today's video, I'm gonna do a deep dive into IP services, technologies like FHRP or First Hop Redundancy Protocol. I'm gonna cover 3 different flavors of FHRP, technologies like HSRP, VRRP, GLBP. I'll then do a deep dive into DHCP, and finally, I'll wrap it all up with a deep dive into DNS. This is going to be an exciting video, I promise you. So grab a beverage of your choice and let's roll. Welcome to CCNA 200-301 course. Today, I'm going to cover Section 4, Part 1 of the CCNA exam, IP services. In particular, we're going to cover IP service galore. Here are the topics I plan on covering today. First, FHRP. Second, DHCP. Third, DNS. Finally, I'll wrap it up with device management protocols such as NTP, SNMP, syslog, SSH, and TFTP/FTP. Let's go. Let's first discuss FHRP. Before we understand what that is, let's quickly take a look at the network architecture and design, because that will help us understand the value of having redundant default gateways. Now, as you can clearly see in our current design, whether we look at the branch site that is at the bottom of the screen or the data center top right of the screen, we have no network edge redundancy. And when I say network edge, it's basically the customer edge router located either at the branch site or the data center. That's what constitutes the edge of the network. Now, in this instance, what's happening is, let's look at the branch site. If that PC wants to talk to the data center server up at the top, there's only one default gateway that it can go through. And if that default gateway goes down, our entire network is hosed. Same thing with the IP phone. It's only got a single default gateway. Return traffic from the data center back to the branch, there's only a single default gateway. When it comes to network, a lack of redundancy is a cardinal sin. You cannot afford to build your network without redundancy. You must account for redundancy. Unless there is a financial reason for not being able to create a network that is fully redundant, that is understandable, but you must let your business owners know the risks involved if they're not letting you design your network correctly. Now, that said, let's talk about a couple of issues with this design. Here are all the single points of failure in this design. Core switch 1, if that goes down, everything goes down. Link between the core switch 1 and branch customer edge 1, that goes down, everything is down. If that router at the edge goes down, absolutely we're down. If that circuit that we have plugged into the customer edge goes down, we're hosed. Moving up the chain. At the data center, default gateway circuit goes down, we're done. Data center's customer edge 1 goes down, we're done. If the link between core switch 1 and CE1 goes down, we're done. And if the core switch 1 melts and blows up, our network goes down. The whole name of the game when it comes to redundancy in networking is eliminating these single points of failure in our network. And that's exactly what I'm going to talk about. So I'm going to keep building on this next. So before we had no network redundancy, now we're looking slightly better. Starting off at the branch, what you will see differently here is that we got redundant circuits plugged into our default gateway. We still have a single default gateway box, but we have redundant circuits coming in now. So if one circuit goes down, our traffic can still continue going through the secondary link. Now at the data center, things are looking much better. Not only we have redundant circuits coming in, we now actually have redundant customer edge routers. That is excellent. And they're also plugged in redundantly into the core switches. So for all intents and purposes, we no longer have any points of failure in the data center, but in the branch, we still have a few single points of failure, and let me point those out for you. Core switch 1 is still a single point of failure. Link between core switch 1 and CE1 is still a single point of failure. And finally, the edge router in the branch is still a single point of failure. But as you can see, by adding redundancy in the data center and also bringing in redundant circuits into the branch, we have essentially reduced our exposure and created a better environment. Let's see if we can still do better than this. Here we have a fully redundant network. As you can see, we don't have any single point of failure. We got in the branch, we have redundant circuits coming in. We got redundant routers plugged into redundant core switches. Same thing happening in the data center, redundant circuits, redundant routers, redundant core switches. It all looks great at this point, but we still have a problem. We have a single default gateway. Why is that? Well, the host operating system, whether you have Mac or Windows, what you have is on that device, under the IP configuration, you can only specify a single default gateway. And that's what creates this unique challenge for us. Because we cannot program redundant gateways on our host operating system, we have to figure out a way to get creative and allow the network to provide that type of redundancy to our end hosts or to our endpoints. What we can do though is we can get around this problem by configuring all hosts to point to the primary default gateway. When the primary default gateway fails, we can manually configure all hosts to the secondary gateway. And when the primary default gateway comes back online, we can go ahead and manually change all the hosts and point to the primary default gateway. Well, I don't know about you, but to me, that is extremely painful, especially if you have dozens of users or hundreds of users in your environment. That is not practical. Unless you're getting paid per manual entry, I would never do that, ever. And what's the solution? Well, the best solution is automation. And that's where FHRP comes into the picture. So now let's talk through what FHRP is. Stands for First Hop Redundancy Protocol. Why is it called First Hop Redundancy Protocol? Well, think about it. In our network, we have these switches are in a layer 2 domain. Whether in the branch or the data center, these switches are in a layer 2 domain. The first layer 3 hop in our network starts at these routers. That's the first layer 3 hop. Hence the name First Hop Redundancy Protocol. The primary purpose of FHRP is to provide default gateway redundancy. As I alluded to on the previous slide, by default, we only have a single default gateway. When we run FHRP, it allows us to alleviate this problem and rectify this issue. And it essentially makes default gateway failover automatic for us. Now, let me logically explain to you step by step how first hop redundancy protocol works. Now, this is a conceptual understanding, so bear with me here. I'm not going to show you the configuration piece. I'm just going to logically show you the steps so you understand how that works. And then after we're done with that, I'll then jump on a CLI and show you how to configure FHRP on a command line. Now, what we're doing here, in order to explain this step by step, we're going to zoom into a branch site that has redundant default gateways. So the first step is that FHRP assigns what's called a VIP, a virtual IP, and it also assigns a corresponding VMAC or virtual MAC to the default gateway routers. Now, what does that mean? So if you guys remember, the problem is on this device right here, I can only have one default gateway. That's all my operating system allows me to do. So how do I allow a single default gateway to point to redundant devices? That's where FHRP comes in. So we take these two devices and we kind of combine them, so to speak, and we create a single VIP, virtual IP, and a single VMAC, a virtual MAC address. And the binding of the two is what FHRP does for us. And this fools the operating system into believing, these endpoints believe that they actually have access to only a single default gateway, but in reality, they actually have access to more than one default gateway. You can actually have more than two if you wanted to, but in most of the networks, you only have two default gateways. Endpoints, which in our case is a PC and IP phone, get their IP and default gateway from the DHCP server. So another thing that's not in this picture here is at work, in real world, of course, we'll have a DHCP server that serves all the clients that are in our environment. Instead of manually assigning all the IPs, we have a DHCP server, and that pushes the configuration down. Endpoints populate their ARP table with this virtual IP and virtual MAC address. When the primary default gateway fails, the secondary takes over. Nothing changes on the endpoints though, because their ARP entries remain the same because it's all virtual IP and virtual MAC. So even if the primary default gateway went away, that's okay, because remember, we did some virtual magic with the IP and default gateway, and that's what allows us to keep ARP entries intact. However, the switches must update their MAC table from the primary default gateway to the secondary default gateway. This is done via gratuitous ARP. So if you guys remember, ARP, what is ARP? ARP is where you have an IP address of the other machine, but you don't have the MAC, but the network in the middle automatically figures out the MAC address for you. Gratuitous ARP is where you proactively update the MAC address table of the devices. And it's essentially an ARP reply for which we haven't received an ARP request. It's a broadcast, not a unicast. And gratuitous ARP is sent, as I alluded to earlier, proactively by the secondary default gateway to assist switches in updating their MAC address table. And when the primary default gateway comes back online, it doesn't automatically assume its previous role by default. However, we can change that behavior by making a change in our configuration. So at this point, this was just a conceptual level understanding. If it doesn't make a whole lot of sense to you right now, don't worry about it. I promise it will when I show you on the CLI how it all works. Now, there are three flavors of first hop redundancy protocol. The first one I want to talk about is HSRP version 2. It's Cisco proprietary. It uses the redundancy type of active and standby. Load balancing is done per subnet. Default priority is 100. It uses a multicast address of 224.0.0.102. And the default hello timer is 3 seconds. And it uses communication port number For IPv4, it uses UDP 1985, and for IPv6, it uses UDP 2029. Moving on to VRRP, Virtual Router Redundancy Protocol. It's defined in RFC 5798, so it's industry standard. So if you had a Cisco device and a Juniper device, you can set up a VRRP and they will be able to communicate with each other and form FHRP. It operates in active standby similar to HSRP. Load balancing is per subnet. Default priority is 100. Multicast address is 224.0.0.18. Hello timer is better. It's 1 second. And communication port, in this case, it doesn't use a TCP port or a UDP port. Instead, it uses IP protocol 112. And finally, we have GLBP or Gateway Load Balancing Protocol. This one is also Cisco proprietary, similar to HSRP. However, the biggest difference with this one is the redundancy type is active-active. Load balancing is done per host instead of per subnet. Default priority is the same as the rest, 100. Multicast here is 224.0.0.102, same as HSRP. And hello timer is 3 seconds, same as HSRP, it's default. By the way, these timers can be changed, and we'll discuss that. And the communication port that it uses is UDP port 3222. Now let's quickly zoom in to HSRP. Stands for Hot Standby Router Protocol. Cisco proprietary, as I alluded to earlier. It allows multiple routers to appear as one by assigning a virtual IP and a matching MAC address. HSRP elects one active router to support data traffic from the endpoints at any given point in time, while the standby routers wait for the active router to fail. So what that means is, let's say if you had 4 routers that are participating in HSRP, only one could be active at any given point in time. The rest will be in standby mode, waiting for the active to go away. There are 2 versions of HSRP, version 1 and version 2. Now, version 2 is better and enhanced compared to version 1. And one thing that I want to let you know is these versions are not backwards compatible. So if you're in version 2, then make sure all the devices that are participating in that HSRP group are part of the same version. Otherwise, you're going to have stability issues and your HSRP is not going to work. HSRP version 2 communicates via multicast address 224.0.0.102 over UDP port 1985. It uses hello packets to talk to other HSRP-enabled routers. Default hello timer is 3 seconds and the hold time is 10 seconds. Typically, the hold time is 3 times the default hello. And if you want to do HSRP load balancing, it can be achieved. You actually have to create multiple HSRP groups. Now, if this last point doesn't make a lot of sense to you right now, it will as I continue building on this. So we'll quickly jump on a CLI to do this configuration. And what I'll show you on the CLI is Bob's PC and Customer Edge 1 and Customer Edge 2 routers. And we'll go ahead and configure HSRP on our devices on CE1 and CE2 to show you how that impacts Bob. So the first thing we're going to do when we do our configuration is we're going to assign HSRP group and virtual IP, and then mirror the config on both default gateway routers. We'll then assign CE1 higher priority so it becomes active and CE2 becomes standby, and we'll also zoom into the HSRP group assignment. Now, if you see the virtual IP address on the screen here, it's 10.1.1.254. And the virtual MAC address in our case is 0000.0C9F.F001. Now, where does that come from? This is the default virtual MAC address on all the devices that use HSRP version 2. And as you can see, I've kind of given you a breakdown of how it looks. So all the elements in red, that signifies the Cisco vendor ID. 9 F.F is the HSRP ID, and then the last portion, 001 in green, is the standby group number. Now, the standby group number changes based on the group that you choose. In our example here, we're going to choose group number 1, so it's going to match exactly what you see here. But if you were using group 2, then the last digit of the MAC address will switch to 002 instead of 1, and so on and so forth. Now that said, let's jump on CLI. So here I am on the CLI. One thing I want to show you on Bob's PC, if I do ipconfig/all, you'll clearly see that on Bob's PC, the IPv4 address is 10.1.1.99. The subnet mask is /24, and here's the default gateway, 10.1.1.254. Now let's jump to CE1 and go ahead and configure our HSRP configuration. So if you recall, the first thing we're going to do is we're going to go to Fast Ethernet 00, and the HSRP configuration is done inside of the interface. So it's an interface level configuration. The first command we type in here is standby version 2. So that defines version 2 of HSRP for us. The next command we type in is standby 1, and this number 1 signifies the group number. And after that, we're going to type in our virtual IP that we want to specify. And what you want to do next is standby 1 priority 254. And finally, we want to type in standby 1 preempt. And what that does for us is preempt ensures that when this router goes down and comes back online, it will assume its role as the king of the hill, if you will. And the priority command, the higher the number, the better the priority. So priority is important because that's how you select or elect an active router versus a standby. So at this time on CE1, we're good to go. And let's go ahead and look at our configuration here. So we'll do show standby brief. And what you see here is that on our Fast Ethernet 00, we belong to group 1. Our priority is 254. We are currently the active router. State is active. Active is local, which means us. We're local. Standby is unknown because we don't have the standby, the secondary router configured yet. And our virtual IP is 10.1.1.254. So let's go ahead and write our configuration on CE1. Now let's jump on to CE2 and quickly get this bad boy configured. So we'll do standby version 2, and we'll do standby 1 IP 10.1.1.254. And just like that, I now have HSRP configured on CE2. And let's quickly look at show standby brief. And let's take a look at that. And as you can see right now, our router on interface Fast Ethernet 0/0, we belong to group 1, priority of 100, which is the default priority. We're in the state of speak. However, we went from speak to standby, which is good because we want CE2 to be standby, secondary, right? Active guy is 10.1.1.252. That is CE1, as you can see here in the diagram below. And standby is unknown right now because I typed in this command before the status change. So we'll redo this command and you'll see this is going to change. And the virtual IP is the IP defined in this diagram here. Now let's go ahead and type in this command again. And as you can see, standby is local, which means we're the standby device right now. And now let's go back to CE1 and see how that looks. And sure enough, now CE1 shows that router 2, CE2, is the standby. Now that said, let's go to Bob and do a continuous ping, and we'll do a ping to 109.10.1.99, which happens to be, as you can see on this diagram here, some public IP address that we're pinging. So this right here is a testament that our connectivity is working end to end because Bob is able to access this public IP on the internet. Now that said, let's go ahead and simulate an outage and bring down CE1 because I want to show how Bob's traffic will automatically switch over to the secondary router. Bob's traffic is currently going through CE1 to get to this 109 public IP, but when CE1 goes down, it should automatically redirect traffic over CE2 to access the public IP. So let's go ahead and do that. And also keep an eye on Bob's PC to the left. The continuous ping is going fine. So we're going to go to interface faster Ethernet 00 on CE1 and simulate an outage by typing in a shut command. Now, watch what happened on Bob's PC. As you can see, we missed a couple of pings, which means we lost a couple of packets as we switched. Now, it's not too bad, but we still lost a couple of packets. We can tweak timers to make that better for us. But in this example, to keep things simple, I'm going to go ahead and continue rolling. Now let's go ahead and bring that interface back up. And if you guys remember, we have a preempt command, which means our primary router should automatically assume its primary role momentarily here. And as you can see, Bob's PC is struggling. It's able to send a packet and then it loses a packet and then it sends a packet again and loses a packet. This is all due to reconvergence that the network is currently experiencing because of the failures that we just had. So as you can see, we still are dealing with convergence issues. And finally, Bob is good to go now because now the traffic is once again going through CE1 as primary. And as you can see, we lost a ton of packets when that happened. In reality, we would want to tweak these timers down to make the convergence faster. Here's a reference to the commands I typed on these routers. You can keep this in your back pocket as you try to replicate this in your lab. Now, a couple of additional pointers. Priority, like I said, in HSRP, election of an active and standby. HSRP router is based on priority. Priority can be defined within the range of 1 through 255. Default priority is 100. Next, preempt. Once again, when this option is enabled on the active HSRP router, when it comes back online, it assumes its primary role. And if you don't have that configured, then if the primary device went down and it came back online, it will never assume its primary role. It will always stay secondary. And finally, timers. Default timers can be changed from seconds to milliseconds, as I alluded to earlier. And one quick tip is we can create another HSRP group for load balancing by creating a VLAN and subnet. Now let me explain what I mean by that. So this is for you to do in your lab environment. And if you run into any issues, feel free to share your thoughts in the comments below. You see, when we have multiple workstations, so we got Bob up here and we got Dan at the bottom here. If we don't do load balancing, both Dan and Bob will always go through this guy, the CE1. And then the traffic will go down this way. Now, it's okay if it's just two PCs, Bob and Dan, but imagine if you had hundreds of PCs on the blue VLAN and hundreds of PCs on the red VLAN. You wouldn't want all of them to go through a single network point because then your CE1 will become a choking point. So in an ideal world, what you would want to do instead is you would want Bob's traffic to always take this path at the top, and you would want Dan's traffic to always take the path at the bottom through CE2 to access the wide area network. To do that, we're going to have to set up what's called traffic load balancing. And that's exactly what I'm showing here. In this case, what I'm showing is that Bob's PC has this IP, this is the default gateway it's using, the LAN subnet that it's part of, /24, and then the HSRP configuration that you would have to do on CE1 and CE2, respectively, as shown on the screen. And what you would want to do is create sub-interfaces on CE1 and CE2. And these links between CE1 and the switch and CE2 and the switch, the reason they're purple is because they're carrying multiple VLANs. They're carrying the red VLAN and they're carrying the blue VLAN. And when you combine red and blue, you get purple. You see what I did there? Pretty clever, huh? Now what we'll do is we'll make CE1 active HSRP router for blue VLAN and subnet via high priority. And the HSRP virtual IP that we'll configure here is 10.1.1.254. And what we'll do next is we'll set up another subnet completely separate from Bob's, and it's going to be 10.1.2.0/24, and you can see all the configuration here. We'll create separate sub-interfaces on CE1, CE2, create different groups, and configure them accordingly. And as you can see, what we're doing is we're basically making the CE1 active for blue VLAN, standby for the red VLAN, and we're making CE2 active for the red VLAN, standby for the blue VLAN. And that's pretty much it. Now, in the interest of time here, I'm going to skip the configuration part. But like I said, if you are configuring this in a lab and are running into issues, feel free to drop your thoughts in the comments below. Now let's quickly shift gear to DHCP. DHCP stands for Dynamic Host Configuration Protocol. The whole reason we have DHCP is it automatically assigns IP addresses to endpoints connected to the wired or wireless network. I don't know about you, but I don't like doing anything manually, right? And especially if you have a ton of workstations and IP phones and wireless devices, it's insanity to manually assign anything. That's where DHCP comes in. As soon as you have those devices come and join the network, they get plugged in or connect wirelessly, they automatically get their IP information. Now, DHCP server automatically provides the following information to each DHCP client, whether it's a laptop, a desktop, wired, wireless, IP phone, regardless. This is the information each device gets. Gets an IP address, gets a subnet mask, gets a default gateway IP address, which we just finished talking about. Typically, that's our first hop redundancy protocol, virtual IP. We just talked about it, so it's very timely. And it also provides DNS server IP addresses. Typically, you would have redundant IP addresses. And here's how it looks. So I took a snapshot of my laptop here, and as you can see here, it's configured via DHCP. It's picking up its IP automatically, subnet mask. The router in this case is the default gateway that we just talked about, right? Which is a virtual IP. And the DNS server in this case is the Google DNS servers that are specified. These are Google public DNS servers, to be exact. Now, here are some DHCP server features that we can configure when we're on the DHCP server. We can define an address pool. So that is basically a subnet, which is a range of IPs. On the DHCP server, we can define reserved addresses. So basically, this is a list of excluded IPs. And I'll show you on the CLI how that works. Address binding. We can also do that on the server, meaning we can have what's called a MAC reservation, meaning a manually defined IP address MAC to a MAC address. Now, why in the world would you want to do that? So think about it. Like at home, for example, for me, I have address binding set up for my network attached storage or NAS server, and I've also got an IP printer. I've got a network printer that I print to. And I've also done the same thing. I have a MAC address reserved for my printer. And this ensures that the IP address never changes. No matter how many times I reboot those devices, they always get the same IP address. Why is that important? Well, the rest of the devices in the network that need access to these services, like the NAS server or the printer that I have, they point to those devices. And as long as the IP address doesn't change, they can always continue pointing to those devices. And another thing we can configure on the DHCP server is what's called a lease time. Now, whenever you get an IP address from a DHCP server, it's leased to you as the client, meaning you're not handed that IP address for eternity. There's a certain expiration date on that IP address after which it just goes away. But if you needed to keep that IP, we can renew the lease. And by the way, this is not an exhaustive list of features on the DHCP server we can configure. This is just a very small yet important feature list that I wanted to share with you. Now let's quickly look at how DHCP works and the DORA process. So here's Bob. He has a laptop. He physically connects to the switch, and we've got a server that's also plugged into the same switch. So how does Bob's PC or laptop gets an automatic IP address from the DHCP server? So first, what happens is Bob's PC sends what's called a discover broadcast, and it's sent to the DHCP server through the switch, which switch basically forwards as all Fs when it comes to the MAC address at layer 2. And we all know what all Fs at layer 2 means. It's a layer 2 broadcast. All the devices will get it. Only the device that understands that packet uses it, everybody else drops it. Now in this case, DHCP server gets that discover request, and it's able to determine that it's intended for the DHCP server because it's coming from the source of all zeros. The DHCP server then responds back with an offer to Bob, and the reason DHCP server is able to respond back to Bob and not any other PC is because it's got the MAC address in the initial discover. So it responds back to that MAC with an offer, and inside of that offer, and if you were to zoom into that offer packet, what we'll see is an IP address and a lease time. Bob gets it. Bob then sends a request to the DHCP server saying, I like your offer and I would like to accept your offer, and here's my request. Finally, the DHCP server responds back with an acknowledgement leasing that IP to Bob, and now Bob is good to go. And this is where the acronym DORA comes in. Discover, Offer, Request, Acknowledgement. It's the first letter in all of these different packet types. If you combine that together, that's called DORA. So that's the easiest way to remember from an exam perspective, because this could very well be an exam question. Now, by default, what ends up happening is Bob is going to get an IP from the DHCP server, no problem, because switches can send broadcasts all day long as they're layer 2 switches, right? Well, what if we have a layer 3 device in the middle, like which we do in this case? Well, what do routers do when they get a broadcast? Routers hate broadcast. They drop it. So the router is going to drop that broadcast, and if Leah down below wanted to get an IP address from the DHCP server, the packets will never make it through. The packets will always get dropped right here. As soon as the packets are received at this interface on the router, they'll get dropped. So how do we fix that problem? This is where DHCP relay agent comes in. So what we do is we set up a DHCP relay agent on this interface pointing toward the DHCP clients. And when the DHCP clients respond or send a discover broadcast, that discover broadcast is received on this interface, and it's transparently then passed along to the rest of the network until it gets to the DHCP server. And the DHCP server consequently is then able to respond back to that device that sent the initial request for the IP address. And that's how DHCP relay agent works. And at this step, what I would like to do is quickly jump on CLI and configure DHCP so you get some hands-on experience. And I'll keep it very simple here. As you can see, we have Bob to the left, The LAN subnet there is 10.0.0.0/24. And to the right of CE1, we got the DHCP server. And the subnet here is 192.168.0.0/24. And a couple of things I want to talk to you about is first the DHCP server config overview. So what we'll do from a high level perspective is we'll specify excluded addresses first. And I'll tell you why we need excluded addresses once I'm on CLI. We'll then define a DHCP IP pool. We'll specify a network, we'll specify a default gateway, and we'll specify DNS servers. This is the server-side configuration. Once that's done, then our client is going to be able to pull the configuration that we have defined on the server. Now, the DHCP relay agent config is very simple. What we'll do is this interface right here that is pointing to Bob, we'll go ahead and specify what's called an IP helper address, which points to the DHCP server, which would be 192.168.0.2. And with that, CE1 is going to be able to take that broadcast from Bob and being able to pass it along to the DHCP server and vice versa. Now at this point, let's go ahead and jump on CLI. Now I've got a pretty interesting lab here for you. All of these devices that you see are actually Cisco routers. For lab purposes, I decided to show you how you configure a Cisco router as a server, DHCP server to be exact. How do you configure a Cisco router to be a DHCP relay agent, and how you can set up a DHCP router to actually be a DHCP client. I thought that would be interesting for you to see, but in reality, in a production environment, most likely would have a dedicated DHCP appliance and a dedicated DNS appliance that provides that functionality to you. But for lab purposes, in understanding the mechanics, this will do fine. So let's go ahead and configure our DHCP server here. So here I am on the DHCP server. I'm going to go to global configuration mode. And the first thing I want to do is I want to go ahead and exclude the range of IPs that potentially might be allocated to devices. So for example, 10.0.0.0/24 network has this .1 allocated to the router. Now that would have to be excluded because CE1 shouldn't be getting any IPs from the DHCP server. These are the IPs that we want to manually assign for a good reason, and that is you don't assign your critical network infrastructure elements automatic DHCP IPs. You want to manually assign IPs so you can route properly and define your access control lists and things of that nature. Whereas your workstations and your laptops and desktops and wired devices and wireless devices and IP phones, all those should get IP addresses automatically. So let's go ahead and define the exclusion first. So IP DHCP excluded address, we'll say 10.0.0.1, and we'll end the range with 10.0.0.20. Now, you can define a much larger range if you wanted to, but for my purpose, 20 is a good number. You can also define another excluded address range on top of the one that I've defined. Let's say if I had another range that was not contiguous, let's say another range was 10.0.0.100 through 120, and this way I'll have an additional range of excluded addresses. But in this instance, this should do fine. Now let's go ahead and define our IP DHCP pool. And basically pool, as the name suggests, is a range of IP addresses that are defined. In this case, within the DHCP pool, we define different DHCP parameters. We'll first start off with the network parameter. We'll say 10.0.0.0/24. As you can see in the diagram below, because that's the network that we want to define for our workstations. What you want to do next is you want to do default -router 10.0.0.1, which is this interface right here, the fast Ethernet 00 on CE1. You want to define that. That will actually be the default gateway IP. And if you guys recall, we just finished our discussion on first hop redundancy protocol. this should be a virtual IP of your FHRP. That's what you would want to define here for redundancy purposes. And finally, we'll define our DNS servers. And what we'll do is we'll say 192.168.0.2. Let's assume our DHCP server is also a DNS server. In reality, that's not going to be the case. You're probably going to have, like I said, a dedicated appliance, or you might actually even have public DNS servers. And let's assume we have another redundant DNS server. Once again, this is a good practice to have redundant DNS servers specified. And at this point, my DHCP server should be good to go. And let's quickly look at a couple of show commands. Show IP DHCP pool. So this shows us that you have a pool called workstations defined. And right now we are not utilizing anything. Our utilization is 0 right now. And the total addresses that can be handed out is 254, which makes sense because if you guys remember, the first IP in the range is called a network address, which ends in .0. That cannot be assigned. And the last address, which ends in .255, that is called a broadcast address. And that can also not be assigned because those are reserved addresses. Hence, we can only assign 254 addresses. Currently, we don't have any leased and all that. And that's pretty much it. So our DHCP server is good to go. Now let's jump on to Bob. As we'll go to global configuration mode, go to fast Ethernet 00, and we'll say IP address DHCP. So at this point, Bob should be able to automatically pull an IP address from the DHCP server. Now let's go ahead and look at that. Show IP interface brief. And we don't have an IP address assigned to us yet. Well, the reason is CE1 needs to be set up as a DHCP relay agent, and we haven't done that yet. So if you guys recall, we go to global config mode, we go to fast Ethernet 00, and on this interface, we're going to define our IP helper address. So we'll do IP helper address, and we'll type in 192.168. We'll point to the DHCP server. And that should be it for our DHCP relay agent at this point. Let's go back to Bob. And Bob should be getting an IP address pretty soon. And here it is. Sure enough, Bob was assigned an IP address of 10.0.0.21/24. And let's go ahead and do show IP interface brief. And sure enough, looks good. Let's look at show interface fast Ethernet 00 so we can see more details here. And as you can see, we have an IP address defined with a subnet mask of /24. Now let's quickly take a look at the DHCP server and see how things are looking. So we'll type in show IP DHCP pool. And as you can see here, it says that it has leased one IP address. Now let's go back to the DHCP server and look at show IP DHCP binding. This command shows us the IP address that has been leased out to Bob, and it also shows the client ID right next to it. And another very important aspect here is the lease expiration that's attached to it. Now, the time is a bit off on this device. This is like the default clock. That's another aspect that I will cover later today, where we'll set up an NTP server to fix the clock on our local device. Now let's shift our attention to DNS. I'll quickly give you a walkthrough of DNS. DNS stands for Domain Name System. It operates on the principle of a client-server model. DNS server provides a name resolution to network endpoints. What that means is DNS translates a host name or a URL, which stands for Uniform Resource Locator, to a corresponding IP address. So, in other words, the whole reason DNS was designed was, as human beings, we're good with remembering names rather than an IP address. For example, instead of going to www.google.com, if you were to type in an IP address, it's nearly impossible that you're going to remember all these IP addresses for different websites. It's a lot easier to go, when I go to Facebook or Amazon or Twitter or whatever. As human beings, that's how our brains are wired. It's a lot easier for us to remember names than numbers. And this is where DNS comes in. DNS takes the host names that we can easily remember as human beings and automatically on the back end correspond to the appropriate IP address and display the resource that we're trying to access. As a best practice, configure redundant DNS servers for high availability or HA. Here are some of the most popular public DNS servers in the world. My personal favorite is Cloudflare. It's actually a pair of DNS servers. Primary is 1.1.1.1 and secondary is 1.0.0.1. They claim to be the fastest DNS servers on planet Earth, and I have found that to be true. Now, next up is Cisco OpenDNS. You have the addresses right in front of you. That's a company Cisco had acquired a couple of years ago called OpenDNS, and it's now become part of Cisco umbrella. And the IP addresses that you're looking at are publicly available for anyone to use, and they provide security services on top of DNS with malware protection and all that. So it's pretty interesting if you're interested in security features instead of just a plain vanilla DNS service. And another very popular public DNS service that a lot of people use is Google Public DNS Servers 8.8.8.8 and 8.8.4.4. They're also really fast, but I've noticed Cloudflare is in its own league altogether, just absolutely earth-shatteringly fast. Now let's quickly discuss what is DNS and how it works. So we talked about what DNS is. Now let's talk about how it works. So we have Bob, and his PC has an IP address of 20.1.1.1, and there's a DNS server on the internet that has a public IP of 40.1.1.1. Now step one is Bob sends a DNS name resolution request. So let's say Bob opens up a browser and goes to www.cisco.com. That's what we call a DNS request. Now, next thing that happens is the source port on Bob's PC, it's also called a private port from a private range of ports, is automatically allocated. Let's say in this case, 49.799. And the destination port, because DNS runs over port UDP 53, is 53 because that's the destination. And the source IP in Bob's case is 20.1.1.1, and the destination IP of the DNS server is 40.1.1.1. Now, a couple of things I want to bring to your attention is, like I said, this at the top is considered a DNS request. The source port and the destination port combined, this is your transport or layer 4, and the source IP and the destination IP combined, this is your layer 3 header. And the information makes its way to the DNS server. The DNS server then responds back to the name resolution reply, and it says the IP address of cisco.com is 80.1.1.1. The source port is its own port. The destination port is the previous port defined by Bob, and the source IP is DNS server's own IP, and the destination IP is Bob's IP, of course. And the final step in the process is, at that point, Bob now knows how to communicate with Cisco.com web server at the bottom right of the screen, which happens to be at 80.1.1.1. And Bob starts talking directly to the web server. It no longer has to go and talk to the DNS server anymore because the DNS gave it what it really needed to be able to communicate with Cisco.com. And then we have the source port. Once again, it's going to be a randomly generated port. Destination port in this case is going to be port 80, which is for HTTP. Bob is going to form a TCP connection, a three-way handshake with the web server. And the source IP is going to be Bob's IP, destination IP is going to be Cisco.com's IP. By the way, this 80.1.1.1 is a fictitious IP. This is not the real Cisco.com IP used for the purpose of this example. Now let's zoom out a little bit and see what the DNS server did for us that we looked at on the previous slide. So here's Bob again. So the step one is Bob types in Cisco.com in the browser. It goes to the internal DNS server, which for majority of the people, it's your ISP server, or it could be the public DNS server I talked about, like the Cloudflare or Cisco or Google. And that server will get your request. And once it gets that request, assuming it doesn't have an answer for it, if it does have that information in its cache, it will immediately respond back. By the way, taking a step back here, if your PC already knew how to get to Cisco.com and there was a cache in the browser, the PC won't even bother going to the DNS server. It will just automatically take you there. But this process happens because we don't have an entry in our local database on our machine. So our machine then goes to the DNS server to see if it's got that information. Now, assuming the public DNS that we're connecting to doesn't have that information either, then what ends up happening is it ends up going to a root level domain server. And it says, look, I got this request for Cisco.com. Do you know where that is? Well, the root level domain server, there's only few root level domain servers, by the way, around the globe. Some big universities actually maintain root level domain servers. There's a handful of them. The root level domain server says, well, I don't know the answer, but I do know the top level domain server who may know the answer to that. And the top level domain servers are .com, .org, .gov, .mil, .tv, etc. So because you're trying to get to Cisco.com, it says that I'm going to send you to the .com top level domain server. Now that server says, well, I don't know exactly where Cisco.com is either, but I do know second level domain server that knows exactly where it's hosted. And at that point, the second level domain server redirects the request to the authoritative server, the actual server where Cisco.com is hosted. And at that point, that server responds back directly to our public DNS server. And at that point, the public DNS server responds to us. By the way, this entire thing that we just looked at, which took me a couple of minutes to explain, this happens in a blink of an eye. It's super duper fast. By the way, this is also known as recursive DNS lookup. Recursive means the request is constantly redirected and it bounces around different hierarchy of servers until the traffic gets to the point where the actual DNS server responsible responds back to our public DNS server and we end up getting an answer for it. And that is DNS for you. Thanks for sticking around. By the way, there's a lot more to this video than what you have seen. In order to watch the entire video, you're going to have to be a little patient because I'm working on designing an entire CCNA course. I'm going to do an official launch in the next couple of months. But until then, I'm going to keep putting little nuggets of the CCNA exam out there on my YouTube channel until the course is ready to be published. Hope you enjoyed today's video. If you did, give me a thumbs up, hit subscribe, and I'll see you in the next video.